Hey everyone, this is Dr. Walker. In this video, we're going to go over an example from v531 on a parallel plate capacitor. In this video, we just showed the equation for the capacitance of the parallel plate capacitor. So now we want to go ahead and derive that capacitance. It's a really good exercise. And the parallel plate capacitor is the most simple case. So we know that capacitance is charge per voltage. And we know that voltage depends on electric field. So the first thing to find the capacitance is we need to find first the electric field. Then we're going to find a potential difference between the plates. And then we can find the capacitance. So let's start with the electric field. One way to find the electric field between the plates of the parallel plate capacitor is to use Gauss's law. Let's go ahead and set that up. E dot dA is equal to the charge enclosed over permittivity of free space. And we haven't done this in a little while, since chapter 6, so let's look at one of these conducting plates, for example the positive one. And we know that the charge is going to be on the inside of the plate, right? Because if you have the other negative plate over here, the negative charge is going to be on the inside because they're going to be attracted to each other. So that's the first thing. And the other thing to consider, which I'm showing in this picture here, is that the electric field is approximately uniform as long as the length of the capacitor here, the size of its plate here, is much greater than the separation between the plates. So as long as it's a long capacitor, then we can just consider the electric field being uniform inside and we don't have to worry about the edge effects over here. Okay, that being said, let's look at a Gaussian surface. For a plate, we like to pick a cylinder or a box. I'll just pick a cylinder. And that's my Gaussian surface over here. And we know that the electric field is pointing away from the positive charge, and it's uniform. So that's good. And it's parallel to the area vector. So we're going to have this circular area here that has an area vector pointing away from it in the same direction as the field. So E dot dA is going to simplify to simply E times A, where A is the area here of this Gaussian surface, so I'll just call it AG just for now. And then we need to find the charge inside the Gaussian surface. Well, that's going to be a ratio of the volume of the charge enclosed within the surface versus the charge enclosed within the entire plate. And instead of doing a ratio of volumes, we can do a ratio of areas. So what we can say is that the ratio of the volume, the area of the Gaussian surface over the area of the entire plate, right, that fraction times Q, where Q is the total charge on the plate. We said in the video that one conductor will have a charge positive Q and the other conductor will have a charge negative Q. So we'll call it Q here. So really ask yourself, make sure that you understand why Qn is this fraction times Q. And then we divide by epsilon naught. All right, now we see that the area of the Gaussian surface cancels out and we get the electric field inside our capacitor is going to be Q per A over epsilon naught. And we don't need to put it as a vector form right now. Let's just say it's going to the right and it's uniform. Now to find the potential difference. We know that when the field is uniform, then the potential difference is given by negative ED for a uniform field. And when we're finding capacitance, we really just need the magnitude of the potential difference because capacitance is charge per potential difference. It doesn't matter which plate is positive, which plate is negative, it's still a set potential difference between the plates. So if we're looking for the magnitude of the potential difference, then we don't need the negative sign. So we now get the electric field Q over A epsilon times D. And we're almost there. Let's bring it over here to the last step to find the capacitance. It's going to be the charge per voltage. So it's going to be Q, and then we're dividing by V, but we can just multiply by the reciprocal. So times A epsilon over QD. And we see that the charges cancel. And we are left with our expression for the capacitance of the parallel plate capacitor epsilon A over D, as we saw in video 531. So I want to go over this derivation. We're going to do a few more derivations for spherical and cylindrical capacitor. The process is the same. Find a field, then find a potential difference, then find the capacitance.